Distance doesn't exist, and I'm about to prove it using the most mind-shattering physics experiment ever. You think that when something happens here, it can't instantly affect something there. Common sense, right? For something here to influence something there, some kind of signal must travel across the space between them. That signal can't go faster than light. So there's always a delay, but quantum mechanics says you're completely wrong. And Einstein hated this so much he spent the rest of his life trying to prove it false. Let me show you what Feynman understood about this cosmic conspiracy that even Einstein couldn't accept. Start with something simple. Two coins. You flip them both. Each has a 50% chance of heads, 50% chance of tails. The result of one flip has absolutely nothing to do with the result of the other. They're independent, random, uncorrelated. Now imagine something impossible. Two quantum coins that are entangled. When you flip the first one and get heads, the second one, no matter how far away, instantly becomes tails. Not probably, not after some delay, instantly. Flip the first coin in New York and get heads. The second coin in Tokyo instantly knows to be tails. No signal travels between them, no communication, just instant correlation across unlimited distance. This should break your brain. This violates everything you think you know about causality and locality. Einstein certainly thought so. In 1935, he wrote a famous paper with his colleagues Podolsky and Rosen, arguing that quantum mechanics must be incomplete. They called quantum entanglement spooky action at a distance and insisted no physical theory should allow such nonsense. Einstein's argument was brilliant and seemed ironclad. If quantum mechanics allows instant correlations between distant objects, then either information travels faster than light, violating relativity, or the objects have predetermined hidden properties that we simply can't see. Since faster-than-light signals seemed impossible, Einstein concluded that quantum particles must have hidden variables, secret properties determined in advance, that explain the correlations without requiring any spooky instant connections. For 30 years, Einstein's argument stood unchallenged. Quantum mechanics worked perfectly for calculations, but maybe Einstein was right about the underlying reality. Then in 1964, a physicist named John Bell changed everything. Bell asked a simple question: if Einstein is right about hidden variables, what experimental predictions would that make? Can we test whether hidden variables actually exist? Bell derived a mathematical inequality, now called Bell's inequality, that any hidden variable theory must satisfy. The inequality sets limits on how strongly correlated two measurements can be if the correlations come from predetermined hidden properties. But here's the kicker. Quantum mechanics predicts correlations that violate Bell's inequality. Quantum mechanics predicts stronger correlations than any hidden variable theory can produce. So Bell had set up the ultimate test. If experiments show correlations that violate Bell's inequality, then Einstein's hidden variables don't exist. The spooky action is real, but it gets stranger, much stranger. In the 1970s and 80s, physicists performed increasingly precise tests of Bell's inequality. They created pairs of entangled photons and measured their properties at distant locations. The results were clear and consistent. Bell's inequality is violated. The correlations are stronger than any hidden variable theory can explain. As Feynman explored in QED the strange theory of light and matter, quantum entanglement is real, experimentally verified, and completely demolishes our classical understanding of locality and independence. Let me give you the specific numbers that should shatter your worldview. In a typical Bell test experiment, you create two entangled photons and send them to detectors that are kilometers apart. Each detector measures the photon's polarization at different angles. If the photons had predetermined polarizations, if Einstein was right about hidden variables, the maximum correlation you could get between the measurements is, but quantum mechanics predicts a correlation of 0.707, and that's exactly what experiments measure, 0.707. The difference might seem small, but it's revolutionary. It proves that the photons don't have predetermined properties. Their properties literally don't exist until measurement forces them into existence. When you measure the polarization of one photon in New York, you're not revealing a pre-existing property. You're forcing both photons, even the one in Tokyo, to choose correlated properties simultaneously across unlimited distance. Think about what this means. The photons aren't communicating. They were never actually separate in the first place. What we experience as separate particles are actually different aspects of unified quantum systems that transcend spatial separation. Here's where it gets even more mind-bending. As Feynman explained in the Feynman Lectures on Physics, entangled particles don't have independent properties waiting to be discovered. They exist as unified quantum systems where measuring one part instantaneously affects the entire system. The measurement doesn't send a signal from one particle to another. The measurement collapses the unified quantum state of the entire entangled system simultaneously, creating correlated outcomes that appear to involve faster-than-light communication, but actually involve no communication at all. When you measure one entangled photon's polarization, you're forcing the entire two-photon system to choose definite correlated properties for both photons simultaneously across unlimited distance. The distance between the photons is irrelevant. They could be on opposite sides of the galaxy, and the correlations would still be instant and perfect. But wait, there's something even more disturbing about quantum entanglement and reality. If entanglement allows instant correlations across unlimited distances, and if every quantum interaction creates entanglement, then the entire universe might be interconnected through quantum entanglement at the most basic level. Every particle interaction creates entanglement. Every quantum measurement breaks some entanglement while creating new entanglement relationships. The history of the universe is a vast network of quantum entanglement connecting every particle to every other particle. The photons hitting your eyes right now are quantum entangled with the electrons that emitted them from distant stars. Those electrons are entangled with other particles in stellar cores. Those particles are entangled with particles formed during cosmic evolution stretching back to the Big Bang. You are not an isolated observer looking at a separated universe. You are part of a vast quantum entanglement network that connects you instantaneously to particles scattered across cosmic distances and evolutionary time. As Feynman understood in The Character of Physical Law, quantum entanglement reveals something profound about the nature of physical reality. What appear to be separate objects are often just different aspects of unified underlying systems viewed from limited classical perspectives. But it gets even stranger, much stranger. Modern experiments have pushed quantum entanglement to extraordinary scales that should completely shatter your understanding of distance and separation. In 2017, Chinese scientists created entanglement between photons separated by 1,200 kilometers using quantum satellites orbiting 500 kilometers above Earth. The correlations remain perfect across that distance. No delay, no weakening. Instant correlation across a distance that light takes 4 milliseconds to cross. In 2019, researchers achieved entanglement between quantum systems separated by 50 kilometers of underground optical fiber, maintaining the spooky correlations despite massive separation and the quantum-destroying effects of fiber optic cables. In 2022, the Nobel Prize in Physics was awarded to 3 scientists who performed the definitive Bell inequality tests. Their experiments closed every possible loophole that could explain away quantum entanglement. The verdict is final. Einstein's local realism is dead. These aren't just laboratory curiosities. Quantum entanglement is revolutionizing technology. Google's quantum computer uses 70 entangled qubits to perform calculations that would take classical computers thousands of years. IBM's quantum network already connects quantum computers across the globe through entangled photons. Quantum cryptography uses entanglement to detect eavesdropping with perfect accuracy. If anyone tries to intercept an entangled photon, the entanglement breaks, immediately alerting both sender and receiver. This isn't theoretical. Quantum encrypted communication networks are already operating in China, Europe, and the United States. But here's what's really mind-bending. If consciousness involves quantum processes in the brain, then your awareness might be fundamentally connected to quantum entanglement networks throughout the universe. As Feynman explored in 6 easy pieces, quantum mechanics applies to all physical systems, including biological ones. The microtubules in your neurons, the protein structures in your synapses, the electron transport chains in your mitochondria, all involve quantum processes. Every conscious observation might create entanglement relationships between your neural quantum processes and the quantum systems you observe, linking your awareness to distant cosmic events through instantaneous quantum correlations. Your thoughts about this entangled universe right now involve quantum processes in neurons that might themselves become entangled with the quantum field fluctuations you're contemplating. Let me bring this all together with something that should completely demolish your understanding of separation and independence. Einstein was wrong about hidden variables, but he was right about one thing: quantum entanglement really is spooky. It violates our deepest intuitions about locality, causality, and independence. But as Feynman demonstrated, the universe doesn't care about our intuitions. It operates according to quantum mechanical principles that transcend classical common sense. Distance is a classical approximation that emerges when we ignore quantum entanglement relationships. At the fundamental level, particles that have ever interacted remain connected through non-local correlations that make spatial separation meaningless. You're not surrounded by separate, independent objects. You exist within a unified quantum field system where apparent separation is maintained by ongoing measurement interactions, while underlying unity persists through entanglement correlations. The space between objects isn't empty. It's filled with quantum entanglement relationships that connect everything to everything else through instantaneous correlations that transcend distance and time. As Feynman understood, the universe is far stranger and more unified than classical physics suggested. What seems like spooky action at a distance is actually the revelation that distance itself is an emergent property of quantum measurement rather than a fundamental feature of physical reality. Tomorrow, when you observe distant stars, remember you're not seeing across empty space to independent objects. You're participating in quantum entanglement networks that connect your observation to stellar quantum systems through non-local correlations that make the universe fundamentally unified despite apparent separation. The connections are real, the distances are emergent, the universe dreams in entanglement, and consciousness participates in making